Here I would like to present an engineering software tool that may be useful to those working with four-wheeled mechanical systems, more commonly known as automobiles. The first part of the application can be described, roughly, as a 3D version of WinGeo. WinGeo was prized for the speed of its workflow, especially next to much more expensive corporate-level packages. You could move a hard point, apply roll, heave or steering input, and see the geometric response right away. This application takes the same approach. You pick a suspension type, drop in the hardpoint coordinates, and the linked metrics follow along as values change. The 3D environment isn't just there for looks, it makes the geometry much more intuitive to read. In WinGeo I would often flip into the offset view to understand what I was looking at. Here, the picture is immediately clear. There are two main input modes, combined roll and heave, and individual will travel. On the side of the screen sits an output data panel, used to choose which metrics appear in the main graphics window. Enabling a metric brings up a simple dialog asking for the label's initial position, expressed as a percentage of the window's width and height. After the initial placement, holding Shift and left dragging moves the label anywhere on the screen. The application remembers each position, so the layout persists across sessions. With the symmetry checkbox enabled, picking left front camber also brings in the right front camber label, mirrored automatically. Derivatives can be toggled per metric and plotted against either will travel or roll angle. A global override is also available. The Interactive Input Controls tab lets you adjust the chassis pose directly and watch the output metrics respond in real time. It's the fastest way to get a feel for how the geometry behaves. For a more structured look at the geometry, similar in spirit to WinGeo's reports and load path file, there is the motion input feature. It defines a sequence of motion steps so you can study how the suspension responds to roll, heave, pitch, and steering inputs. You enter motion points for heave, roll, pitch, and steer, click Add Point as many times as needed, then fill in the input values. Points can be connected with linear or cubic spline interpolation. To make this a little more convenient, I also added direct mouse editing, hold the left button and drag points around. The default sample count is 100, but it can be overridden with any value, provided it isn't lower than the input point count. More samples give a smoother animation. Each input sequence can be saved to a file and reused later. Running the motion profile produces results in two views, live metric values on screen while scrubbing through the replay, or any chosen suspension metric plotted for closer analysis. The plot x-axis can be percentage of completion, will travel, or any other log channel, so this supports both standard time history plots and x, y style analysis. There is also visualization of instant center construction lines and markers, geometric roll center and pitch center lines with their markers, each toggled by its own checkbox, with separate controls for front and side view. Overall, a lot of effort went into keeping the interface simple, intuitive, and easy to customize. The application is still very much a work in progress, and I haven't reached the UI polish stage yet. One drawback of WinGeo was that, although it was theoretically possible to work with front and rear axles at the same time, in other words, at vehicle assembly level, the implementation was not especially convenient. At the top of the project tree there is a design library. This is where the user adds components that may be needed in the project, suspension files, springs, dampers, and so on. Below the design library there is a vehicle assembly entry. Here the user assigns the components from the design library that should be used in a specific vehicle assembly. The front axle remains at the global origin. The rear suspension is transformed according to the specified reference distance. In assembly mode, still inside the geometry design workspace, the front and rear suspensions are attached to a common chassis, and pitch input becomes available. Track log data replay is also much more straightforward, and removes a lot of the manual preparation that was previously required in WinGeo. The workflow is simple. In the Motion Input Editor, the user clicks Import, opens a log file, chooses a lap, and the application takes care of the rest of the process. At this stage, direct import of Emotek logged files is already implemented, and exported .csv and .txt files are also supported. WinDerib support is next on the list after Emotek's native .ld, mainly because Bosch ECUs and DDU loggers are so common in FIA GT3, GT4, Formula 3, and many other categories. Once the file is loaded, the application parses the data and tries to identify the damper travel and steering wheel angle channels automatically. If the channel names are unusual, or automatic detection does not find the right signals, the user can simply assign the channels manually. Then the user clicks Create, and the software builds a motion input that drives the suspension model from the logged data. This allows the engineer to replay and analyze what the suspension was doing on track. Once track replay results are available, the user can analyze logged and simulated channels together in the analysis workspace. Adding simulated outputs such as dynamic camber and tow to the standard logged data gives the engineer deeper insight into tire and chassis behavior, and helps explain the car's performance on track. The next step is to add more templates, so the software can cover more suspension layouts, starting with the ones people actually use most often. I'm also adding more small analysis tools and workflow utilities. Not necessarily glamorous features, but the kind of things that save time when you are doing real design work. One example is an IC lock tool for working with anti-dive and anti-squat. If the instant center lock is enabled and the user moves the rear chassis pickup of an A-arm in Z, the software automatically moves the front pickup in Z as well, keeping the instant center in the same place. It is a small thing, but these small things add up. And they prevent a lot of unnecessary clicking, which is always good for mental health. The goal is simple: if a competitor has a useful feature, this tool should have it too, but with a smoother workflow, faster setup, and a cleaner user experience. The next big milestone is the optimization module, which is already in development. I have to admit, I'm not a huge fan of optimization in suspension design when it is used as a black box. But it is an important feature commercially, and since tools like OptimumG include it, we need to cover that ground as well. The next module has the internal name Load Transfer Rig. This is where the application moves from kinematic suspension geometry into dynamic multi-body simulation. The vehicle assembly now has mass, inertia, constraints, elastic elements, dampers, and time-dependent applied loads. In other words, this starts to move into the same general territory as tools like Atoms, SimPack, and similar multi-body dynamics packages, but with a workflow focused specifically on race car setup and suspension design. Each major component has its own mass and inertia. The upright, brake caliper, brake rotor, and related hardware are represented as a lumped mass. The damper is modeled as two bodies, the damper body and the damper shaft. Springs are represented as one-way force elements with free length. Anti-roll bars are modeled as torsional springs connecting the left and right sides of the torque tube. The blade is represented as a lever arm fixed to the tube, so changing the effective blade length changes the stiffness seen at the suspension pickup point. The goal of this module is to help the user understand how setup parameters affect tire normal loads under dynamic conditions. That includes springs, anti-roll bars, dampers, ride heights, and suspension geometry changes. This is useful for both existing vehicles and new suspension designs. On existing cars, there may already be alternative pickup points available. Many transaxle gearboxes, for example, provide multiple control arm mounting positions. This module is meant to make those options easier to evaluate, with fewer guesses and fewer heroic assumptions. The basic idea is simple. External accelerations are applied to the model using D'Alembert's principle. So instead of simulating the full vehicle motion around a track, the logged or prescribed acceleration field is applied to the multi-body model as equivalent inertial loading. The model also uses a special rig tire. In very basic terms, the tire forces at each corner are linked to vertical load and acceleration. The longitudinal tire force equals the vertical load times the longitudinal acceleration, and the lateral tire force equals the vertical load times the lateral acceleration. This is an oversimplification of the actual implementation, but it explains the main idea. Longitudinal acceleration on the driven axle is applied according to the drive torque distribution. Braking force is applied according to brake bias, calculated from brake pressure bias, front and rear piston areas, and effective disc radius. Tire vertical stiffness can be represented either as a linear function, or as a table if the user has measured stiffness data at different pressures and camber angles. A possible workflow can start with something as simple as a setup pad simulation, predicting corner loads, ride heights after camber changes, how one alignment adjustment affects the others, and so on. Even this simple case, if done properly, can save a team a significant amount of time at the track. A dynamic multi-body model is the closest practical modeling approach we have for this type of mechanical system. It is still a model, of course, so it will never be perfect. But it captures much more of the real system behavior than simplified static calculations. For suspension geometry design, I personally do not know another tool that allows this kind of quick study of how geometry affects roll stiffness and tire vertical loads in a proper multi-body context. In very expensive tools like Atoms, this normally means setting up a dynamic event. That is possible, of course. But it is not quick, and saying that it is not especially convenient would be a very polite way to describe it. For quick evaluation, there is an interactive inputs tab where the user can enter any combination of ax, I, and steering. The user can run either equilibrium mode, which is basically a quasi-static event, or transient mode, where the acceleration ramp time can be defined. The metrics update live on the screen, so the user can immediately see how design and setup changes affect the result. It is a quick way to change a parameter, check the response, and decide whether the idea is worth a deeper look. For a more detailed study, the user creates a load profile. Right-clicking the load profile in the project tree opens the load input editor. It follows the same general logic as the motion input editor, but here the x-axis is time or distance, and the inputs are accelerations rather than imposed suspension motions. Creating a manual load input is simple. The user sets the simulation time, adds ax, I, and optionally AZ points, adds steering points, and saves the file. The load input then appears in the project tree. From there, the user opens the simulation dialog, chooses the result file name and destination directory, sets the logging frequency, and runs the simulation. The run is animated in the main graphics window, which gives a useful first sanity check. Visual inspection is still a good first-pass filter, because it helps confirm that the model is behaving sensibly before going into detailed plots. After the run, the results file is added to the project tree. The user can replay the animation at different speeds, or open the file in the analysis workspace and plot hundreds of logged simulation channels. The user can then make a design or setup change, rerun the simulation, and overlay different runs to compare the model response. Things become more interesting with logged data replay. As in the geometry design module, the user imports a logged track session using one of the supported data formats discussed earlier. The difference is that here, the application replays the real on-track acceleration history through the full multi-body model. The user can simulate the full lap, or zoom into a specific area of interest and run only that section. At each time step, the rig calculates tire loads, springs and damper forces, anti-roll bar loads, and many other simulation channels. The engineer can then study what was happening in a specific braking zone, corner entry, apex, or any other part of the lap. More importantly, the user can change a setup parameter, rerun the same logged session, and compare the response directly. There is one important limitation. The setup change affects the simulated tire loads and suspension response, but it does not feed back into the original logged chassis accelerations. The acceleration history is treated as an imposed input. So this is not a full closed-loop vehicle simulation. But for setup and design work, especially when reliable tire data is not available, it is still a very useful tool. It gives the engineer a way to estimate how tire loads change, when those changes happen, and how springs, dampers, anti-roll bars, ride heights, and geometry all contribute to the result. It also makes damper influence visible in a way that is not really practical with a purely quasi-static simulation. The module also provides per-member load extraction. Forces and moments at suspension links and joints are available throughout the simulation. These loads can be used for engineering checks, FEA input, fatigue assessment, or simply to understand the load paths through the suspension. This is one of the natural advantages of a full multi-body formulation. Constraint loads are direct solver outputs, not just post-processed estimates. Let's use the final corner of this lap as an example. Right out of the box, the simulated results already correlate reasonably well with the logged track data. The largest error is in the rear damper positions. In this case, that makes sense. The data comes from a GT4 car with a relatively small rear wing, and the front splitter does not appear to generate much aerodynamic load. This brings us to one of the major directions for the software, state estimation. The idea is to use the model to reverse engineer unknown parameters or inputs. The first simple version of the aero estimation toolbox is already implemented. The user selects a straight section of track, and the estimator treats suspension movement that cannot be explained by logged accelerations as aero-induced movement. It then adjusts total CL and front aero percentage until the simulated damper displacement better matches the logged data. The next stage will extend this into a more detailed estimator that derives a ride height-dependent aero map. For this vehicle and data set, the Stage 1 estimator gives CL equals 0.247 and front aero percentage of 0%. The result is written into the project tree. Now we can run the model again with the estimated aero load and compare the results. Straight line correlation improves significantly. The remaining difference in damper travel traces is mainly driven by track surface, because up to this point the simulation assumes a perfectly flat road. To address this, we go to the bump profile page in the load input editor. At this point, the feature is still in its first stage. The user first clicks Create Damper Input. This creates reference damper displacement channels from the logged data. Then the user clicks Create Bump Profile. The system compares the logged damper displacement with the simulated damper displacement, and uses the difference to estimate 4 road height channels. In simple terms, we treat the logged damper movement as the real suspension response. The simulation explains part of that response through acceleration, aero load, and setup. Whatever is left over is interpreted as the road input. The remaining difference is treated as an estimated road input. The result is 4 road Z channels. The next step is to rerun the same load input, but now with the reconstructed bump profile added to the simulation. Then we compare the simulated and logged results again. Even at this first stage, the reconstructed road surface already captures many of the track-induced features. There is still one area after the corner apex where the overall shape of the damper traces matches, but the compression magnitude at the right rear does not correlate well. The mismatch starts around the apex of the corner. If we add the throttle trace, it becomes clear that the divergence begins when significant drive torque is applied. At this point, I should mention that the logged data I have is about 5 years old. I do not know the exact damper settings that were used on the car, or which damper curves corresponded to those settings. More importantly, the scanned data I have for the front and rear suspension does not include a reliable relative Z alignment between the front and rear. To me, this damper position discrepancy after throttle application looks like the modeled rear suspension has more anti-squat than the physical car had when the data was recorded. As an experiment, I lowered the front attachment point of the rear lower A-arm and reran the simulation. The correlation immediately became much closer. Does that prove the model now matches the physical car suspension? No. I do not know that. But it does show that the multibody model responds in the way we would expect the physical car to respond to that setup change. The bump profile can also be edited manually. This gives the user a simple way to adjust the estimated road input and improve correlation in specific areas where the Stage 1 reconstruction does not capture the track surface accurately enough. Here is an example of the simulated output after manually adjusting the area where the vehicle drives over the curbs on corner exit. Next, I want to describe the current damper model used in the software. Again, the intention is to make the workflow feel closer to working with a physical car. With that in mind, I created a dedicated shock dyno workspace. This is where damper files are created, edited, and calibrated. In the first panel, the user assigns a file name and defines the available adjusters. The user also enters gas pressure and rod radius, which are used for gas spring force calculation. After that, the user chooses the authoring route. The simpler and faster route is create PVP model. There are two methods in this branch: segmented damping and force velocity table. Segmented damping is the quickest way to define the damping law used by the damper model during simulation. When the engineer selects this option, the software shows the adjusters that were defined in the damper model tab. The user can activate the compression branch, the rebound branch, or both. Then the user enters the current adjuster position and defines the curve using velocity range, damping coefficient, and knee area width. When the user clicks Generate Active Setting Curve, the curve is plotted in the viewport. In this way, the engineer can create separate bump and rebound curves for each adjuster position. There is also a Generate Adjustment Sweep option. The user creates two endpoint curves, chooses the interpolation method and spacing, either linear or growth ratio, and the software generates the intermediate curves automatically. So, in this workflow, the user creates a damper properties file containing multiple curves, corresponding to the defined adjusters and their positions. The second method is the force velocity table. This one is more direct. The user enters velocity and force values manually, or imports table data from dyno results or from tools such as Öhlins VRP. After saving the damper file, the user can add it to the project design library and assign it to the current vehicle assembly. If the damper file contains multiple adjuster positions and corresponding curves, those adjusters appear in the vehicle setup section of the project tree. The engineer can then adjust the clicks, so to speak, in the same way they would on the physical car. The next branch is the extended dynamic model. This one is for engineers who want to go a bit deeper. It is well known that clean peak velocity plot curves are not exactly what the damper is doing in reality. Actual damper force does not simply follow the ideal PVP curve. This branch is designed to import raw dyno data and reverse engineer the measured behavior, including hysteresis effects. Here, a one-dimensional solver is used to produce a damper response that is closer to the real measured response. With the extended matching tools, we can try to reproduce actual damper behavior. There are several tuning panels: series spring and damping, low-speed bleed, valve lag, branch trim, and so on. I have to admit, this is not a simple model. The number of parameters is fairly high, and many of them interact with each other. It took me a couple of hours just to start developing a feel for the common patterns and get to this kind of rough correlation. The user adjusts the parameters for individual velocity runs, and then saves those matched runs as calibration points. During runtime, the software interpolates between the saved calibration points and produces damping forces that are much closer to what a physical damper would produce. When the model is saved, all calibration points are stored in the damper file, and the model is marked as extended. When this damper file is assigned to a vehicle assembly, the system parses the file. If it contains active extended model data, the corresponding checkbox becomes available in the project tree. This means the engineer can directly compare load transfer and contact patch load variation with and without hysteresis effects. I do not want to pretend that this completely replicates physical damper behavior. But at the very least, it gives a practical way to compare an ideal PVP-based damper model with a model that includes internal compliance and dynamic hysteresis effects. This was a short overview of some of the features that are already implemented in the software. There are quite a few existing items I did not cover, and I also did not go into future development and expansion plans. That is a separate topic, and this video is already long enough. For promotion, besides the usual channels, I am planning to create a dedicated YouTube channel. I would start with a few foundation videos on tires, then move into basic vehicle dynamics topics like load transfer and damping, using the software and more advanced visualization techniques to explain the material. After that, I would start posting practical case study videos. These would show different aspects of the software in real use, and would also serve as training material for users. So, that is the current state of the project. Thank you for taking the time to watch it, and I would really appreciate any feedback, questions, or suggestions.